Please go ahead. No, yes. No, it's unmuted.
Okay.
Okay, it works.
Okay. So good morning. I'm Gabriel from the Astronomical Institute of the Czech Academy of Science. I will present this work titled "Origin of Kappa-Cygnid Meteor Shower," and from this I would like you to keep in mind my goal here, that is study the origin of this meteor shower, and also the structure that I will try to use. Sorry, I try to use in this presentation. That I will start analyzing the stability of the region where this meteor shower is coming from, and then I will use the results for this for doing some backboard simulations that is important for set up the time boundary conditions for my simulations. Then I will do my simulations, some results, and with these I will have a kind of hypothetical comet, because this is the hypothesis that I'm using here, that the meteor shower is coming from a comet that we don't know. And then I will use this hypothetical comet to compare with the known comets to try to find a possible parental body. Sorry. Okay. Okay, so with the stability, I'm using Magno. Well, I will not have time to explain very well this, but this is a map for how the orbits are is being unstable. So here we just keep in mind that green is a stable orbit, red we are going for chaos in this case, okay? So in the top left panel, we see the more standard for solar system. Here, I can point there's no problem with the, okay. So in the blue box, we have where the meteor shower is coming from. So we have the zoom here, and we see that it's a very chaotic environment, but this is for the zero inclination. And actually, this meteor shower has a high inclination that we can take as average 35 degrees as inclination. And we see that considering this inclination, we will have a little bit more stability on this region that this meteor shower is coming from. So for a more convenient way to plot this, you will see in the next slide why. I'm now using the inclination and the perihelion distance for finding this region. So again, we have here in this blue where this meteor shower is coming from. And now we can compare with the observed meteors from this meteor shower. So this plot came from the Borovicka 2025, where he identifies some groups of meteors in this meteor shower, some groups in these structures in this meteor shower. And we can see more or less the plot here, how is the stability of this region and where we are the groups. We will focus here in the group 1. And we can see now where the group 1 is in my map of stability. It's actually around chaotic structure, like a thickness. So this shows more or less that we are expecting an unstable region, that maybe we can have some stability for some time, but not for longer time. Because of this, we need backward simulations to see how confident we can be about periods before that we can simulate the comet. So these are the backward simulations. So I have 1,000 clones on the area of this meteor shower, and then I integrate backwards, and I have here the maps of the density of these clones along this simulation. In black, we have a mean of the orbit elements of this meteor shower, just to have an idea on the mean. And we see that the blue area, that is, we have more dense region of clones. When we have this blue, is more indicative that we can simulate on this area. This more or less for all orbital elements, it goes more or less well until 2000 years ago. And more important, the longitude of last sending node that will say to us exactly more when the meteor shower is arriving on the Earth during the year. So it also, we have around 2000. It's a good number for starting the simulations. So now we go for the main part of the simulations. I have this plot I need to explain before starting the video. So we have 3 panels above. All of them indicate are the same thing, but with different zooms. So we have the zoom on the hypothetical original comet on the left panel. In the middle, we have the inner solar system. We can see, the inner solar system. And then we have a zoom out in the right panel. And in the bottom panel, we have I'm using an angle actually that is considering the IRFC frame. I'm using this to compute this theta angle. So I have this angle on a inertial frame to see all the planets. That the 4 planets are here. These lines above. And you also can see the Jupiter, and then we can see the particles moving around the solar system. In the y-axis, we have the distance, the heliocentric distance, and the color of the particles shows the distance from the Earth plane. So this is important because we just can have meteor showers when this stream cross the green line, and it's going to the dark when we have a short distance from the Earth plane. Okay, initially the simulations go a little bit slower because my frame is day by day, because I'm ejecting the particles. Each day I'm ejecting a amount of the particles that follow the mass loss of Whipple model. And then we can see faster after the first passage the evolution of this stream. Okay, very interesting, but let us see what we can have after. So here I'm showing the particles of this stream that collide with Earth. I'm considering the one helisphere from Earth. And then in gray, you can see the meteors observed. And in different colors, we can see the particles by the year that they are arriving. We can see that these showers, the shower that I'm generating with the simulations, is going very far from the region of the meteor shower indeed, the meteor shower observed, right? But the blue part is touching that. So let us redo the simulation. Well, wait, let me explain before, if I have time, why this is happening. Okay, in the beginning, even 100 a year, 80 years, we still don't have a connection between the stream and the Earth orbit. But with 245 years, we have this connection. And now, so you can see in the middle that it's crossing the Earth plane in this moment. So we can start having meteor shower. And this is a very good behavior for having a meteor shower. But when you go further, this is spreading a little bit. In 443 years, we still can have meteor showers because it's touching the green line and it's still dark. But after that, like 1,500 years, we have dark dots. Okay, dark dots around the green line in different moments. So we have the meteor shower, because of this spread of the particles, is drifting along the year. So let us, I'm just did a simulation a little bit shorter, 500 years, to see if this could have a better behavior, and this could more or less explain the meteor shower that we have now, but it still shows that this meteor shower could drift. So now we have, okay, it's like not so far backwards, like 500 years or less, 200 years, something like that. Let us compare now with comet. So using these 3 different methods, I choose these candidates. Well, for using Drummond, the best candidate was the P 2017 Leonard, and using Osborne, the best candidate are Giacobini Zinner, that also is mentioned on the paper from Borovicka. But in both cases are not very conclusive candidates for the parental body. So these are my conclusions, and I think I don't have time for the conclusions, or?
There are 30 seconds, so
Yeah, okay. The is very unstable, the region. A comet is plausible, but it's the ejection of this, the cometary activity could happen in few years ago, in 200s, inside 500 years. Also, maybe this meteor shower can drift along in some decades along the year. No conclusive similarity has been found. And as the next step, we could implement more than just one ejection. Sorry for this much.
thank you very much.